Thank you all for coming. And before I forget, thank you very much to Midwest.io for having me back. I was privileged enough to speak at their first iteration of this last year and had a great time and was excited to submit again, although I did encourage them not to pick me because I had been here last year and I figured they should branch out a bit, but here I am nonetheless. So we are here to talk about time today. And specifically, we're not talking about time zones and leap years and leap seconds and September 1752 and Easter and the other Easter. That's a different talk. In fact, that's probably a whole series of talks. We are here to talk today about logical time. I am John Daly. I work for a company named Basho Technologies. We write a distributed database called REAC, and distributed databases are a big place where time and causality come into play. Thus, I've been exposed to a lot of this theory and practice over the last few years. Quick note to lunch is coming up at the end of my talk. I will try not to get between you and lunch. So if I seem to be going a little fast, it's because I don't want to be between you and lunch, but please feel free to interrupt, especially if I jump the rails. I'm very good at tangents. It's very easy to get me off track. So pop up, ask questions. Otherwise, what I'll plan on doing is if you have general questions that don't involve, hey, John, I have no idea what you're talking about, go ahead and try to save them for the end, and we can talk after, while other people are free to go get their lunch, and we can talk about your questions. So the question is, why are we here at all? And I appreciate everyone who bothered to show up. So causality and coordination are such trivial concepts on single machine applications. It's something you never even think about, really. However, as soon as you introduce a second machine and a third machine, causality and coordination become much more complicated. So complicated, in fact, that we've been at this for 40 years or so, trying to address these problems, or even longer, and we're still finding new areas of research and new ways to improve our handling of this issue. If I can use an astrophysics analogy here, this is much like the two-body versus three-body problem in physics. Two-body is trivial, three problems a whole mess. In computers, one server is fine, two servers or more is a real challenge. So let's start by talking about the simplest, non-trivial problem I could come up with. Two clients, two servers, key value store, and two concurrent attempts to set the same value. Rather, set the same key with different values. So the question here is, in a scenario like this, who would win? Now, you may say, John, this is obvious. The last one to arrive would win. And that's a simple enough heuristic. We can certainly apply that. In this case, the 242 right would arrive after the 237 right, and we'd say, well, our balance must be $300. So then the question becomes, given that heuristic, what happens if both rights arrive at the same time? So RFC 677, one of those internet RFCs I bet you've never read, is written by BBN, my former employer, way back in the day, 1975 or 73, somewhere in that time frame. They came up with a set of rules for keeping a distributed key value store in sync. And one of those rules is that you implement a tiebreaker here. Each object, each operation in your system is tagged with a logical timestamp. It's tagged with not only the physical timestamp, but also the name of the server. And you just pick an ordering of your servers, and that one wins. So in this case, B is greater than A, so we pick the right that arrived on server B, and we call that the winner. Now, one of the questions that will arise out of this is, when it comes to business logic, is just blindly picking the last right to arrive the right choice? We'll talk more about that. So there are any number of lists on the internet of things that programmers believe that are not true. This is a subset of things that programmers believe about time that are not true. I have personally been bitten by, well, several of these, but the most notable one was number 16. Time on the server clock, time on the client clock would never be different by a matter of decades. Yes. Astonishingly enough, my very first IT job, I was, among other things, supporting Windows 3.1 clients connecting up through dial-up. And we had a customer in northern Indiana, I'm from Indianapolis, customer in northern Indiana, and some of their desktops simply refused to connect to our system. And so I was heading up to Chicago anyway, so I dropped in and tried to figure out what in the world's going on. Well, it turned out that some of their desktops had somehow been set at least 10 years in the future. I don't remember the exact date, but it was far enough in advance that DOS could not accurately represent the date. It was 2000 something, and nobody was quite sure what it was. I think it was at least 10 years. At any rate, we reset the clocks back, everything worked fine. So yes, server clocks, client clocks are rarely in sync. Server clocks themselves are rarely in sync. And this is a vital problem to try to solve. Now you may say, okay, well, we've got NTP, why are we talking about this at all? Fact of the matter is, NTP is a great tool, and like all tools, it fails. Firewall rules are set up wrong. Daemons are not configured to start at boot. Daemons give up their, throw up their hands and give up if the synchronization drifts too far. NTP can also roll your clock backwards, which is a terrible, terrible thing. We'll talk more about that. Yes, I have heard of Spanner. For anyone who hasn't, Google published a paper on their time synchronization strategies, which involve bajillions of dollars, specialized hardware, atomic clocks, GPS clocks, highly reliable networks, their own server hardware, all this with the goal of trying to synchronize clocks across their entire environment. Well, even their TrueTime API, which they supply, still gives you an error range anytime you ask for the current time. So even Google, throwing all this money at the problem, still doesn't know what time it is. Okay? Time is a hard problem. This is not something that's trivially solved, even with all the money and resources in the world. Leslie Lamport. Who here has heard of Leslie Lamport? Okay, good percentage. I am embarrassed to admit the only reason I knew about Leslie Lamport before this job was LaTeX. He's the LA in LaTeX, which is the macro programming language for tech that a lot of people use. Leslie Lamport is a lot more than the author of LaTeX. He is a Turing Award winner, and he is a distributed systems pioneer. In the mid-70s, he wrote this paper, which has been cited more than all but one other computer science paper in the history of computer science. Time clocks and the ordering events in distributed system. And Leslie recognized that hardware clocks were bad. Of course, in the 70s, I would imagine hardware clocks are even worse than they are today. There was no NTP yet. And he was looking at the general problem of how do you distinguish time in an intelligible way in a distributed system? Obviously enough. And he had a key realization. In this case, we have three discrete processes. Those processes are characterized by internal events. Those internal events are all running on the same hardware, so within each process, you can trivially order the sequence of events, right? On one computer, we know what happened first. That's easy enough. Between processes, the communication is messages. And Leslie realized that these messages provide us an event horizon or event boundary, a point in time where we can say, P1 happened before Q2 because P1 sent a message and it arrived at Q2. So you cannot send a message after it arrives, right? We have some basic laws of physics, even though physics itself struggles to tell us what time it is exactly, we do know that messages arrive after they are sent. So that provides a strict ordering. We know that P1 and Q1 are concurrent, not necessarily parallel. Parallel implies things are happening at the same time. Concurrent just says they happened and we don't know which one happened first. That's one primitive definition of the two terms. P1 and Q1 are concurrent. We can't really say anything about their ordering other than they happen maybe roughly the same time. But regardless, Q1 happened before Q2, P1 happened before Q2. So Leslie builds up the system in order to share a global clock. That global clock is no longer a physical timestamp, it's a simple counter. Each time you send a message, you send your counter along with it, and the process that receives that message, if its counter is behind yours because it hasn't committed enough events in its timeline, it will advance that counter. So in this case, A is on 7, B is on event 4. When A sends this message, B picks it up, says, well, A has seen 7 events, so I need to move mine at least to 8. There is a vital word that does not appear in Leslie's document, but shows up in a lot of other papers around clocks and time and logical time. Monotonicity, and in this context, means time always goes forward. Time should never go backwards. Obviously, Windows 3.1, I had to set the clocks back in time. You don't want to do that for a database server, right? If you set a relational database that's actively processing transactions, if you rewind that clock, bad things happen. Never set a clock backwards. Has anyone actually done that and been burnt by it, out of curiosity? Hey, we have one lucky. I've never been burnt lucky enough, but I have to admit, in my misspent youth, I would, in fact, set clocks backward, because I didn't know any better. It's a bad idea. All right, 1988. Lamport's ideas have been around for a bit. We'll actually rewind to an earlier paper here in a few minutes. Colin Fidge in Australia takes Lamport's ideas further, and he defines this concept of vector clocks. So each process in your system tracks a global state, not in terms of a single counter, but it's the last timestamp it knows for each of the other processes in the system. And every time it sends a message, it will share that global state with whatever process is on the other end. And the remote process can then take a look at that, compare it to its notion of what the timestamps are, and push everything forward. So in this case, B did not know that A had advanced to event 6, so it pushes 6 forward. B's own event counter gets incremented because the receipt of a message is another event in its life cycle. And it pushes C's clock forward to 13 because C sent the message, and that sending the message constitutes another event. So B can go ahead and advance that to 13. So now at the, say we're troubleshooting or we're trying to understand how the system arrived in the state, we have a much more comprehensive history, and we can do a better job of analyzing what the order of events across the system was, even if the physical timestamps themselves do not align. Now, you may be asking yourself, how would I troubleshoot log files that have these monotonically incrementing counters, right? What does 12 mean? What time did that happen, right? Was there a solar flare yesterday at 1 o'clock? Maybe I should be looking for something there. So, Strange Loop. Anyone been to Strange Loop? I hope some of you have. Excellent. So Strange Loop in St. Louis every year, one of the best technical conferences you will ever attend. John Moore from Comcast gave a great talk this year about clocks, specifically about hybrid clocks, trying to marry logical clocks and physical timestamps, and use that marriage in order to A, keep physical clocks better in sync across your cluster, and B, have something that operators can actually look at in a log file and figure out what in the world's going on. So physical timestamps are tremendously useful, but they're not the focus of today's talk. So you may have noticed I pulled a fast one on you. I started by talking about the problem of data synchronization, of choosing a winner in conflicting rights, and I jumped to global state order. All right? It turns out that these are very similar problems. They have very similar solutions, but they are in fact separate streams of research for the most part, although people are trying to unify the two now. So let's go back in time a little bit to 1983. So a team from UCLA was writing a network operating system called Locust. And Locust has two big ideas for this. You take all the computers in the network and you expose a global process state and a global file system state. So you can manipulate processes on any machine in your network, and you can edit files that are stored on any machine in your network. Incidentally, I tried to work on this same problem many years ago, and we got nowhere near as far as they did. There are some very hard problems to solve here. So this paper was specifically focused on the problem of network partitions. The paper itself introduces version vectors, not to be confused with vector clocks, although many people do, including Riak, our database, got that name wrong. We use version vectors, but we call it vector clocks. But as importantly, it talks extensively about what partitions actually mean for a network. Now, one of those myths that programmers believe about networks is that partition networks, or network partitions are rare. That could not be farther from the truth. Network partitions are evil, they are pernicious, they are ubiquitous, and they're extremely difficult to troubleshoot. Network partitions don't have to be bidirectional. You can have server A able to talk to B, and B can't talk to server A. Good luck troubleshooting that one. And good luck writing software that can account for that, right? I mean, what do you do when you have two servers where only one of them can talk to the other one? Flaky network cards. Broadcom, cough. Flaky network cards can cause this type of partition. We even plan for partitions, mobile clients, right? You have mobile clients that can operate independently of the network. Offline mode, that is a partition. Anyone old enough to have used NFS in an industrial environment 10, 15 years ago? Anyone remember what happened when the server went down? Basically, your computer was wedged. NFS is a classic example of a protocol that at least used to be, I don't know nowadays, but used to be terribly, terribly intolerant of network partitions, and yet they happen all the time. So version vectors that this paper introduces. So again, they were focused on, in this case, global file state. So the problem they were trying to solve with this is, if I edit a document on both sides of a network partition, how do I reconcile that after the fact? Now this is a simple case. We have a document which has been edited on servers A and B on the left-hand side here. 2 edits on server A, 1 edit on server B. The other copy of this file has been edited twice on A, twice on B, and 5 times on yet another server that the first file had never seen C. Well, the right-hand side here, this file, version vector, as I said, vector clocks, version vector is local alike. Version vector dominates the other one. It is considered to completely supersede the other one because it's seen all the edits that the one on the left has seen. So we can trivially say, well, the one on the right is the authoritative document because it's seen all the edits the other one has, we can throw the other one away. That's the simple case. Sadly, things are rarely so simple. This is another more common case where edits have occurred on both sides of a network partition. We had 4 edits on server A and 1 on B on the left. We have 2 on each on the right. If we can automatically merge that, that's great. Let's say we automatically merge it on server A, and thus there's another edit that occurred on A, so we bump that 4 to 5, we bump the B value to 2, and we're done. Problem is that frequently those edits are not so easy to merge. By the way, my clock never started. How am I doing? 10 minutes? Okay. 10 minutes before lunch kicks in. So let me take a break here because I've gone way faster than I expected because of the whole lunch thing. And are there any questions at this point? Am I moving too fast for questions? Okay. So this paper in 1983 posited a lot of things that are only now being thoroughly researched. One of them is this concept of automatic merges. And this leads me to CRDTs. Now, depending on who you ask, the C can mean a lot of different things. The RDT stands for replicated data type. The C can stand for conflict-free, it can stand for commutative. I think there's at least one other interpretation of C. But the short version of this is that each of these is this common concept that you can define data types that are resilient to network partitions if you constrain them to operate in certain ways. Counter is a trivial thing to describe. So if you set up your counters such that you are always incrementing the counters and never decrementing them, well, if you have a network partition and you merge them later, you just add up all the increments and there's your new value. So that's an extremely trivial case of a CRDT. Now, there are some trade-offs here for counters specifically. If you store each individual request, that history can grow quite large. If you don't store each individual request over time, you have an idempotency problem, right? Typically, you expect, or you can think, that if you were to increment a counter and you get a timeout, well, the question becomes, what do you do, right? Timeouts are much like network partitions themselves. They are effectively partitions, are awful. How do you cope with the fact that you got a timeout? Do you send the operation again, or do you hope that the system handled it properly? So if you do store a complete history of all your transactions, you can deal with idempotent counter updates. You send another update, the system recognizes, hey, I've seen this before, I can just drop it. But then your simple little integer counter occupies, hundreds of kilobytes or megabytes, et cetera. So there's a significant trade-off of time versus space here. What will commonly be done is you can store a limited history of your counter and hope that no one issues a repeat request after you've purged those entries. Garbage collection and deletion are very difficult problems to solve in distributed systems as well, and looks like we might have time to talk about those. Sets are another relatively simple concept. If you have two sets on two servers, you just lump them together and you've got your merged set. Easy enough. The problem with sets comes in, you want to start deleting items from a set. Well, how do you delete an item from a set? More importantly, if you have a set and an item is not in that set, how do you distinguish the two scenarios of, hey, someone deleted it versus that set never saw it? How do you know which of those two cases? All right. Well, the nice thing is about these logical clocks, they can capture causal history. So we can actually keep track of, say, tombstones inside the set, and we can know at what point in the logical global state that object was deleted. And so if we get conflicting objects in the future, conflicting versions of the set, we can tell, was this entry added to the set before or after it was deleted on the other side of the network partition? Maps get even hairier. If you can imagine, on one side of a network partition, someone is adding a value to a nested set inside a map. On the other side of the partition, they're removing that set entirely from the map. Who wins, right? Well, one of the constraints of CRDTs is you have to define those heuristics. You have to choose for yourself. If you have a concurrent update with a remove, which one wins? Typically, in the interest of protecting your data, we'll default to go ahead and keep it as opposed to deleting it, because clearly someone thinks that that value is still relevant and someone's trying to update data. So this fundamental idea of leveraging these logical clocks in order to preserve causality in a distributed system is actually turning into new programming languages. So the Berkeley team, Joe Hellerstein and his crew, are working on a language called Bloom. And it's basically, it's part of it. One of the implementations is an add-on to Ruby. Don't ask me more than that. I'm not sure how it works. But it's smart enough to actually understand logical clocks and causality. So when you're issuing requests around the network, the language itself can take care of some of these conflicts for you. Chris Micklejohn, former coworker of mine, extremely active in CRDT research, is working with Peter Van Rooij on a programming language called LASP, which again takes this core concept of, it's actually based on lattice math, semi-lattices. I have no idea what that means. Please feel free to share them after if you do. But in any case, taking these core concepts and turning them into entire systems that can handle this type of logic for you. So I'm sure there are at least a few of you who have been out there thinking, this all sounds way too complicated. I have Zookeeper, I have Raft, I have Paxos. I have ways of coordinating all these updates to objects, updates to records in my database. Why would I need logical clocks at all? Well, one of the challenges with a strong consistency protocol such as Zookeeper or Raft or Paxos is that partitions are not trivially handled. They depend on a majority of the servers agreeing on a value, which is fine if you're on the side of the network partition that has the majority of the servers. If you're on the other side of the network partition, what do? Do you read a stale value? Can you update a value? No, not with a properly implemented strong consistency model. There's a lot of overhead to coordination. How many have seen The Martian? Please tell me everyone has seen The Martian. Oh, wow, okay. Those of you leave here tonight, go see The Martian, okay? It is a fantastic movie. One of the more obvious exposition points is near the end of the movie is someone asking about whether mission control can help them with a rescue operation, and the obvious answer is no. They're, 27 minutes away, however far away Mars is from us. Strong consistency, coordination, centralized coordination takes time, right? In a cluster, it's not so bad. If you're talking about coordination with someone on Mars, that's obviously a lot more challenging. And it's not necessary, okay? We've all grown up, I've grown up in a world where relational databases dominate data storage, right? I mean, that's just, you throw Postgres or MySQL or Oracle at a problem and your problem is solved. But the truth of the matter is that for a lot of uses, for a lot of big data uses, you don't actually need strong consistency. You don't need to know at every moment in time exactly what the canonical version of this piece of data is. If you're doing airline scheduling, for example, and you want someone to reserve a seat, okay, there's no reason to shut down the system because you've got a network partition. If you give two people the same seat, you apologize to one of them. Maybe you give them a refund, doubtful, but some sort of a credit towards your next flight. But there's no reason to shut down the whole system just because you have a problem in your network, right? So strong consistency, the notion of checking in with a central repository and making certain that you can actually do what you want to do is just extra overhead that in a lot of cases not necessary. I mean, think about banks, right? Financial services for millennia relied on eventual consistency, this notion that I will give you a sheet of paper that says I give you some amount of money to be applied against this other bank on the other side of the world. All right, there's no central coordination for all this, right? I mean, even today, if the ATM network breaks, there's no reason to prevent you from taking $200 out of your bank account, even if you can't talk to the server for the bank. And the bank knows where you live; they can get that $200 back from you. So central coordination is useful, but it's not required for a lot of scenarios. But I will say this, if you're going to use strong consistency, if you're going to deploy a distributed system where you need to coordinate changes, use Zookeeper, use Raft, use Paxos. Don't roll your own, please. For all that is holy, do not roll your own consensus system. Ask Kyle Kingsbury. Show of hands, anyone know who Kyle Kingsbury is? Excellent. So Kyle Kingsbury is a fellow, I don't know if I recommend you follow him on Twitter or not, because he mixes his personal life with his professional life quite extensively on Twitter. But he is a phenomenally smart guy, and he spends his time basically breaking data systems. He breaks etcd, breaks Riak, our database, Cassandra, Mongo. Well, I don't know if he even bothered breaking Mongo. Mongo's broken. He spends his time stress testing databases in the presence of partitions. And you'd be amazed how few of the software applications that we rely on for day-to-day business don't actually handle partitions correctly. They claim that they're strongly consistent, but in fact they're not. Even if you do take Paxos or a Raft or a Zab and apply it, make sure you apply it correctly. But better yet, just delegate. Set up Zookeeper in your environment and let it take care of this work for you. Consistency is hard. Other things that we could talk about: garbage collection and deletion. I mean, so let me use React as an example. We talked a little bit about the problem of tracking deletions from maps, where you have to. How do you know when an object was deleted? That's a more general problem with distributed systems. React works very hard to make sure your data is always available, which means that frequently, if you try to delete a piece of data, it may resurrect itself in the future because we've tried too hard to protect your data. These are all simple things that we never think about on a single system image, but when it comes to the distributed system, these are all hard things. Oops, I'm going the wrong direction, aren't I? So that was it. It's about lunchtime, but any questions before I let you go? Please, somebody ask me a question, or unless I think I bored you all to tears. Yes?
Why did you mention Mongo is broken?
Why did I mention Mongo is broken? This is being recorded for the internet. Suffice it to say, use Postgres with its new JSON support. Mongo has a lot of challenges when it comes to distributing its software across multiple servers. There are a lot of consistency problems. There are a lot of data loss problems. There's an old joke on the internet, migrating away from Mongo is trivial. You just wait long enough and it loses all your data anyway. That joke didn't come from nowhere. It's not the most robust system. I'll just leave it at that. Yeah.
You mentioned that it's assumed that a single machine has no problems, but do you see these same problems with multiple cores, multiple disks, memory?
So as CPUs get more complex, things like branch prediction and many other things that I'm completely clueless about because I'm not a hardware guy, actually, yes, coordination and consistency do become more problematic. In fact, I saw Kyle give a talk somewhere where he specifically mentioned that in order to have a linearizable, so big buzzword, linearizability, serializability, are critical terms to define properly when you're talking about databases. But he described the process needed to do a truly linearizable register on your hardware, which involved locking the GPU and the CPU and I don't know what else. So yes, at the hardware layer, that is becoming more problematic as we try to impose more parallelism. But I hope that we as developers really have to worry about that. Yeah.
Your conflict resolution slides always show two machines. So like suddenly you realize you have version A and version B. If you have 1,000 machines, do every two of them resolve conflicts between themselves?
So the question was, I showed some obviously very simple examples. If you have lots and lots of machines, do you do conflict resolution at a global level, or do you do it between individual servers? That depends on your software, to be honest. I mean, you certainly can do both. If you have enough servers and it takes long enough to distribute data around the cluster, you probably want to do it locally and then keep merging as they distribute around. Now, the strategy that a lot of people take is sharding data. So even if you have 1,000 servers in your database cluster, any given piece of data does not reside on all of those servers. It resides on a subset. And so it's usually a lot simpler problem to solve because you've only got 3 or 4 or 5 servers where that data actually lives. That's definitely, one of the reasons to throw that many servers at a database problem is because you have more data that fits on a single server. So typically sharding happens whether you're aware of it or not. Okay, food, lunch. Thank you all so much. And thank you to the Midwest.io team. They've been great.